Okay, cool. Can you see my my screen correctly?
Yep. Yes.
Okay, cool. So hi everyone. Today we are very happy and honored to host Yuqian. She's a fifth-year PhD student at the Computer Science Department at UT Austin, working in the Learning Agents Research Group with Peter Stone. And she's been working on building wide intelligent projects, and she's currently the team leader of the RoboCup at Home team, which is, if you haven't followed it, go and follow this challenge. It's very interesting. Yeah, with that being said, I'm gonna pass it on to Yuqian.
Thanks for the introduction. I'm gonna share my screen now. Okay, hopefully it's working.
Yes.
Cool. Well, thank you for inviting me to give this talk. I'm Jiang, and I'm very excited to present our work towards task planning and learning for general purpose service robots. Just a little bit more about myself and the robots that I work with. I'm a PhD student, currently finishing my 4th year and about to start my 5th year, like mentioned, and I'm advised by Professor Peter Stone. Have been working on the Building Wide Intelligence project, where we have a fleet of these mobile robots in our computer science building. I'm also the current leader of our RoboCup at Home team. We just finished in the 3rd place in a virtual competition this year. But usually the competition uses these physical HSR robots, and we also got this new lab space that looks like a home environment in our new robotics building. So that's very exciting. And so these are the service robot platforms that you will see in this talk, even though they have slightly different target environments and different capabilities. We have been building one planning framework for both of these robots and environments. And today I will talk about our work towards this framework. So to build a service robot, of course, you will need a bunch of capabilities like object recognition, manipulation, navigation, natural language understanding, and so on. And we've seen a lot of recent progress in all those areas, especially with deep learning-based approaches. But for a general purpose service robot, it's also essential to be able to reason about the task and sequence these skills when given user requests like bring me coffee. And I'm generally interested in closing this gap between specialized robot skills that were tested in lab conditions and scalable, robust, general purpose service robots that can work in realistic environments. In general, there are 2 classes of approaches to this problem. There's symbolic planning or automated planning that generates a sequence of actions based on a model or a description of the task and actions. The advantage is that we get a natural decomposition of a complex goal into symbolic actions. Of course, the disadvantage is it needs a domain description and it lacks adaptability if the model is wrong. There's also machine learning, which can be model-free and can work on raw sensory input, but it requires lots of data or experience. So the high-level research goal is that we would like to combine the strength of symbolic task planning and machine learning methods in this framework to reason about high-level actions and adapt to the real world. And we, in general, we approach this question from 2 directions. First, we will address challenging scenarios for robot task planning or task motion planning. Scenario 1, suppose the user asks the robot to get an apple, but the robot does not know where the apple is. We have introduced an approach to plan with those unseen objects. Scenario 2, on the way to deliver your apple, the robot runs into another robot in the corridor. When there are other robots in the environment, they can have conflicts like this, blocking each other in the corridor, and they can form synergies, like they might, one of the robots could go ask for help, to open a door or something. And we've developed a framework for the problem of multi-robot planning with conflicts and synergies. Scenario 3, there could be many valid paths for the robot to bring the apple to you, and the dynamic environment changes the cost of those plans. So we've proposed the task motion planning framework, which iteratively plans and learns the costs of navigation actions. And even though these scenarios or challenges may seem a little disjoint, or maybe they can be individually addressed by other techniques, our goal, again, is to build a unified planning and execution system so that a general purpose service robot can handle all those scenarios. First, I will present our work on planning in the open world with unseen objects. This was joint work with Nick Walker, Justin Hart, and Peter Steele. When you get user requests like, get me an apple from the kitchen, if you know where the apple is, it's easy. You can just use existing symbolic planning approaches to generate a plan like this. However, if you don't know where the apple is, it's difficult for existing task planning approaches because most of them adopt this closed world assumption, and which means that everything the robot needs to accomplish is already represented in its knowledge base. But the real world in general will violate that assumption. At any time, the next command the robot receives might refer to an object that is not currently in its knowledge base or the initial state of the planning problem. But in this scenario, since we're already interacting with the user, we can try to extract that information from the user. So our motivation is to reason and plan in the open world to solve user-specified tasks. And we want to leverage the user's implied hypotheses of unseen objects so that we can just use generic closed world planners. And we also like to do diagnostic reasoning about invalid hypotheses when the robot has made observations in the real world. And of course, knowledge reasoning and planning techniques have been widely applied to service robots. Our work is directly motivated by a test in RoboCup at home, where the robot can be given incomplete and erroneous commands. Also, open world planning is not a new area or concept. There are many kinds of openness of the robot's knowledge or the planning domain, and some of them have been studied. In this work, we target this common scenario where the robot hasn't seen something that the user knows about and can therefore form hypotheses about those objects based on what the user is saying. So here's an overview of the steps in our approach. First, we close the world by representing unseen objects referred to by the user as hypothetical objects. Then we formulate any hypotheses implied by the user, and we model special realizer actions to allow feasible plans be generated with hypothetical objects. And we propose a diagnostic reasoning approach to identify hypotheses that are inconsistent with observations made during plan execution, so the robot can have useful information to report back to the user. The problem formulation looks very familiar for anyone familiar with task planning. The only difference is in this case, we have an open world where the information necessary for the goal can be missing in the initial state. And we're trying to generate a plan that's a sequence of actions that satisfy the goal condition. Here is a visualization of our knowledge representation system that's sort of a core component in the whole solution. The representation has instances and concepts that have unique IDs in a database. So an instance is like when the robot saw a concrete instance of a ketchup bottle, and there's also the concept of the ketchup bottle or the concept of a table represented. And those things are linked together by attributes that describe relations between entities or can store data about them. Like, for example, this water bottle is placed on the dining table.
A quick
Then-
question, sorry.
Sure.
So do you build this knowledge representation, or is it given to you? Do you have these attributes basically beforehand, or does the agent, as it goes and explores, it builds this graph?
This is partially built by the agent using its, we assume there's already like a perceptual module that can like do object detection like YOLO, and part of those concepts are sort of given. And so this is a hybrid of what's already given and what the robots detect in the environment, like those instances are all detected.
I see, thanks.
Cool. So we introduced the following algorithm that closes the planning world with hypotheses. First, we create a new instance for each unseen object, and we have to model the inheritance relation with its object class and the hypothetical concept. And then each hypothesis can be added to the knowledge base with hypothetical instances as references to unseen objects. Like if we think this apple can be in kitchen, and we can have this can be in hypothetical apple in kitchen. And it's important that when we describe the goal condition, unseen objects are referenced using their object class, not the instance. This allows the planner to use the hypothetical instance to generate feasible plans, but replace them with real instances afterwards. And like I said, the realizer actions are modeled to correspond to physical perceptual behaviors that the robot can perform, like scan surface. And we model the action effects to be that these actions turn hypotheses into concrete attributes and relations. Like if before executing scan surface, you have can be on hypothetical apple on dining table, and after in the planning domain, the effect of scan surface is that it turns can be on to is on, which is a concrete relation. However, execution will never actually produce observations of the hypothetical instance, but it will observe real object instances, maybe of the same class, maybe of some other objects, and they will all be populated into the knowledge base. So that here's a quick demonstration of a successful execution of the get me an apple from the kitchen task. The robot goes to every surface in the kitchen, replans if the apple is not there until it finds the apple and picks it up.
Quick question.
Yeah.
Sorry. How does that grasping work?
So for this one, this was a couple of years ago. It was a pretty basic heuristic grasp planner, and with just extending the arm towards where it finds the object. So nothing really interesting there. Just from the perspective of this is just focused on planning in this work.
I see. And then for do you have any do you use any machine learning models for incentivizing exploration, or having agent better explore the scene, or this is planning based?
This part is planning based. This is after the robot takes the user request, but I will talk about something that's like machine learning driven to discover the environment. So very good question. So if there's no apple in the kitchen, we engage a diagnostic rule that attempts to deduce the negation of a hypothesis based on the robot's knowledge. For example, if a hypothetical object cannot be in the kitchen, if all surfaces have been scanned and no such object is found. And we formulate an optimization query which seeks to maximize the number of valid hypotheses. We were doing this with answer set programming and the Klingo solver, so this was kind of straightforward to do with the optimization query. And here I will show a demonstration of using this diagnostic reasoning rule. I think maybe I forgot to enable sound when I share the screen, so but it will
no,
be
you
captioned.
did. We can
Okay.
hear it. Yeah.
Cool.
I could not complete the task due to inconsistent hypotheses. From your request, I assumed a hypothetical apple at the kitchen, but that turned out to be false.
So, okay, very simple demonstration there. In summary, we propose the approach to do planning and reasoning in the open world for service robots that represent the user's hypotheses to enable like feasible plans to be generated and replanning or monitoring during plan execution. And we demonstrate the ability to handle a realistic request that requires the robot to plan with unseen objects and to identify invalid hypotheses. So now we move into a larger building environment where there are multiple robots moving around and completing user requests. This was drawing work with Harao Edition, Jiang, Guni Sharon, and Peter Still. This is just a visualization of two robots, actually discrete plans, but visualized this way. And as you can see, they were likely to meet each other in the corridor. Sometimes the corridors are not wide enough for them to pass each other. And without coordination, they will just see each other as large obstacles and both will turn around. However, if we try to address this problem at the planning time, we can predict that there will be a collision, and we can adjust one of the robot's plan so that adapts to the other robot's plan. They do not have this conflict anymore. Or they could realize synergies, like if they both need to go somewhere their shortest path may involve opening different doors, but if they realize if they know about the other robot's plan, one of them could go ask for help, and one of them could just wait for the door to be open, and therefore minimizing the total plan cost of these robots. And so we formalized the multi-robot planning with conflicts and synergies problem. The input is again the planning domain, and for each agent, we have to model the distribution of action duration. Since robots can easily get delayed by other obstacles, and we want to be able to predict basically the probabilities of how some synergies or conflicts can happen. And we need a cost model of conflicts and synergies. And of course, initial state and goal state. And the output is the set of plans, one per robot, to minimize total expected costs of actions and interactions, including conflicts and synergies. And solving this problem optimally is NP hard, and therefore we want to avoid going into the combined state space of all the robots. That way we can scale to the number of robots. So our approach at a high level is to compute a single agent plan at a time that's dependent on other robots' plans. And so we never have to consider the combined state space. And we do this by modifying the objective function according to other robots' plans. Basically, we model interactions via conditional costs, including expected costs of conflicts and expected costs after realizing synergies. And then we can add these conditional costs into the objective function, and we minimize total expected cost for each robot. As a simple example, again, with the two robots, we will see that they might have a conflict, and we can model the probability of this collision times like a predefined cost of this collision to each of the robots' planning problem. And then the blue robot might discover this other path that does not have this conflict with lower total expected cost. So there's like this very simple algorithm for iterative interdependent planning. We just plan for agent 1 and plan for agent 2 depending on the plan of agent 1 and so on. And the problem with that is the ordering of the agents matters. Like, for example, as you can see, agent 1 will never have a chance to adapt to the other robot's plans. And if that's like the one agent that's causing all the problems, causing all the conflicts, and will never have a chance to correct that. So we proposed an algorithm called increasing dependency, IIDP, where it's inspired by other approaches, but basically we have defined the dependency parameter alpha to represent how much we consider other agents' plans. And in each iteration, we increase this alpha so that we increasingly consider other agents' plans. And the effect that it achieves is the agent that has the lowest cost to switch to a different plan will switch first. And then the ordering sort of gets resolved naturally. We had some results in the gazebo simulation with 2 robots, and it's sort of straightforward to look at. Here we plot the cost of robot 1, the cost of robot 2. The red circles represent the increasing dependency algorithms results, and the blue squares are from just planning independently. And we can see that having this increasing dependency coordination makes them sort of avoid those conflicts and have lower total cost and lower variance. This approach has also been implemented on the real beta bots. And here is an example where the 2 robots realize the synergy. One of them goes to ask for the door to be open, and the other one just follows through. So that was the work on multi-robot planning with conflicts and synergies. Next, we consider the problem of task motion planning in a dynamic environment. This was joint work with Fangkai Yang, Shiqi Jiang, and Peter Still. So again, we're considering mobile service robots in large environments like buildings. And to plan for tasks like deliver coffee to Alice's room, we not only have to plan at the symbolic level, but also need to integrate a motion planner that generates paths in a continuous space. Usually, such feasible plans are not unique, and we want to minimize the plan cost so that the coffee is still hot when it gets there. Why is this a challenging problem? Well, first of all, there could be many feasible plans. In this case, like there are many doors to go into that target room, and the environment changes. Some doors are always closed, and there could be crowds of people moving. So the problem which we're trying to solve is how to generate low-cost task motion plans and adapt to domain changes, such as crowds of people, changing furniture layouts, and closed doors, which are not practical to model accurately at planning time. And basically, there were 2 compelling approaches. One is the task motion planning algorithm, or TMP, for robot navigation. Basically, it uses the motion planner to estimate costs of navigation actions, and the task planner uses that information to iteratively improve the task level plan. There has also been integrations of task planning and learning. This example approach here uses real action costs from execution to inform the task planner. So what we wanted to do was basically to combine both of these ideas into one framework. In this framework that we proposed, there are 2 planning and cost learning loops that receive action cost estimates from both the motion planner and the environment. Here we look at the inner loop. It's a complete task motion planning algorithm. First, the task planner generates the task plan. Then the motion planner evaluates the motion cost of each action. And then the learner updates the costs for the task planner. And this loop terminates when the task planner cannot find a plan with higher quality or lower cost. with respect to the costs estimated by the motion planner. And just to illustrate, there's a simple example. The task planner might say, go to door one, open door one, go through door one. And the numbers in the parentheses are initial cost estimates of those actions. And the motion planner will evaluate each of those navigation actions and might discover that going to door one, the path is longer than expected, and it will take like 20 units of something. And then in the next iteration, the task planner can reevaluate all the feasible plans and finds another one, like go to door two, open door two, and I'll go through door two. And then the motion planner can evaluate all of them again. And maybe this time it will confirm those estimates, and the task planner won't be able to find a better one, and the inner loop terminates. So after it's generated a plan, it will get executed in the environment, and the learner updates action costs using experiences from those executions. And then the inner loop can use the learned costs to generate an improved plan next time it's required to plan. So to continue our last example, maybe opening door two takes a very long time, and the learner will update the cost of those actions, and then the inner loop task motion planning can decide on a different plan next time. So the essential component here in this framework is the learner, which integrates feedback from both motion planning attempts and real executions. Basically, we treat each action cost it receives as a sample cost and use it to estimate the true cost of that action by an exponentially weighted moving average. Next, we've evaluated the TMP-CL approach with just the task motion planning or task planning with cost learning approaches that I mentioned earlier. The experiments were conducted in a room-to-room navigation task using the gazebo simulator. And basically the setup is that there are 3 competitive plans of this task, and the environment is different from what's modeled by the task motion planner. So the robot needs to adapt to the optimal plan, which goes through the door that's usually open. And the second plan has the shortest navigation distance, but it goes through a bunch of doors that are usually closed and require additional time to open. And then the third plan is also short in navigation distance, but the door takes a long time to open. We ran all 3 methods for 40 episodes, repeated 50 times. Here are the learning curves. As you can see, TMP-CL, the blue curve, and TP-CL, the green curve, both converge to the practically optimal plan. But TMP-CL were able to converge much faster with the help of the motion planner. TP-CL without the motion planner has higher variance, and a simple TMP planner does not learn from executing in the environment. To visualize the results better, we plot the distribution of how many times each of those competitive plans or other plans are executed by each method. And again, we see that TP-CL has to try out many logically valid plans, and TMP executes the plan with the shortest navigation distance always. And here I will show a video demonstration on the real robot. The setup is similar to what happened in the gazebo experiments. Doors take a long time to open, and sometimes some places are crowded.
And the robot has access to this map beforehand,
Yes.
right? Yeah.
Yes. The only thing that it doesn't know is like those factors that could influence how long it takes to execute each plan. So the rest of the video is basically a quick run through of those executions happened in the outer loop of the framework. And basically, by the seventh time it executed, it was able to adapt to the best plan. Okay. In summary, we introduced the TMP-CL framework, integrating both task motion planning and learning for adaptable service robot navigation tasks. Experiments show that the framework combines the strengths of both task motion planning and task planning with cost learning algorithms. And in future work, we would like to extend the framework to mobile manipulation tasks, which has different set of challenges. But the high level idea is that we want to learn from both motion planning attempts and real execution experience. So that was the first part. I will just quickly introduce this other direction of our research. In general, we aim to develop RL methods for suitable service robot problems, especially continuing tasks that are understudied but not uncommon in long-term deployments of service robots. And we also want to leverage reasoning and planning to improve sample efficiency. In the interest of time, I would not go into details about these papers. And for this first one, at the high level, we're interested in this continuous area sweeping problem, where the high level goal is like mentioned earlier, that the robot goes around the environment, service the environment efficiently when it does not have an active user request. So in its idle time, so that it can perform cleaning or updating its knowledge base. And we formalized the continuing area sweeping problem as maximizing the average reward in a semi-Markov decision process. And we introduced a deep RL algorithm for such a setting. And that's just a cute animation for the setup of this problem, basically. And the continuing area sweeping problem motivated us to study continuing tasks and the average reward setting better. So that leads us to the next contribution. Again, I would not go into details, but I guess just to introduce the problem, in continuing tasks, it's particularly important to avoid long stretches of informative exploration. And reward shaping injects advice and guides exploration by providing extra rewards. Since manually writing down those rewards can be non-trivial, and we wanted to automate construction of the shaping function from like a user given advice. But advice is not always correct. We also want to ensure that imperfect advice cannot prevent learning the real task. And one approach that gives this guarantee is potential-based reward shaping, which guarantees that the optimal policy is not affected, but it has not been studied in the average reward setting. So in this work, we first extended the potential-based reward shaping to the average reward setting and provide an approach to construct the potential functions from temporal logic specifications. And our main technical results were of proof that the optimal policy can still be recovered with this potential-based reward shaping in the average reward setting. And empirical evaluations showing that the method improves learning performance and is robust to imperfect advice.
How do you process the advice? Basically, is it a template-based sentence, or can it be in any form?
It's template-based. We sort of assume that it's already in the form of a temporal logic specification, like always clean a kitchen. So those are things easy to model. So that was our series of ongoing efforts towards building high-level planning functions of general-purpose service robots. These methods will enable robust and adaptable task motion planning in dynamic environments, as well as continuous area sweeping as a background task to efficiently update the robot's knowledge. In cases where multiple robots operate in the same environment, they're able to adapt the high-level plans to avoid collisions and form synergies. And that's all. I guess I have lots of time for questions. So, yeah.
Thank you very much. Thank you. This was very interesting, and you did a great
Thanks.
job explaining it in a very understandable way for people who are more on the computer vision and embodied AI side and not very
Great.
familiar with the task and motion planning. Yeah, thank you so much. Do we have any question from the audience? Cool. I think I asked a question then. So I was wondering for the exploration phase, for the beginning where you still don't I think it was the first project that you mentioned that if you're looking for an object that the agent has never seen. So the exploration using ORL methods have been studied a lot in the embodied AI. I was wondering if you've tried any of those to see how well it works in this setup, or whether there is any benchmarking against any of the ORL methods or learning approaches.
I see. So I guess those methods will work well if you don't already have hypotheses from the user. Or like if there are further things missing from your planning domain, like if you don't know all the sort of surfaces that are in the kitchen, so like part of your map is missing or something, and or you don't even know what a kitchen is. I guess in this case, we sort of rely on having a model and just specifically targets what the user might know about, and sort of having the user guide us to explore. So yeah, it will be very interesting to like having all those methods combined to the same framework to address all those scenarios, but that wasn't considered in that particular work.
I see. Very interesting. Okay, cool. If we don't have any questions from the participants. Okay, great. Thank you so much for joining us today and accepting our invitation. It was great talking to you, and I really, really hope to meet you soon in person in the conferences.
Yeah, me too.
Yeah, thank you. Bye.
Bye.